break of day, the factory awakens. The arrival of the heavy haulers signals the start of another shift in this massive industrial operation. These serial numbers track the ingot from the smelter to the finished product, ensuring quality control at every stage. Using the handheld scanner, the operative verifies the batch number, ensuring complete traceability. The raw materials arrive here, massive stacks of metal ingots ready for processing in this highly efficient industrial environment. Using X-ray fluorescence, the technician verifies the precise composition of the alloy directly on the factory floor.
Extreme temperatures are required to test the durability of the metal, pushing the alloy to its absolute limits.
The high-resolution macro scanner sweeps across the ingot's unique identification code, capturing the data instantly. As the temperature soars past the boiling point, surface contaminants are violently ejected, revealing the raw metal structure beneath. Positioned at the furnace loading area, these ingots await the intense heat that will transform the raw material into refined steel. This automated rail system carries the freshly cast ingots directly into the furnace, where temperatures exceed 1,000 degrees Celsius. The newly cast ingots begin their slow journey into the searing heat of the chamber, a critical step in the forging process. The internal temperature rapidly climbs, stabilizing precisely at 1,200 degrees Celsius, crucial for the transformation process. The raw ingot is heated until the crystal lattice begins to shift, rearranging the atoms and transforming the very nature of the metal. Utilizing immense hydraulic power, the gripper secures the glowing ingot, ready to transfer the molten metal to the next stage of production.
This automated process ensures maximum efficiency, while keeping workers safely distanced from the intense heat of the newly cast ingot.
Utilizing immense pressure, the forging press slowly shapes the superheated ingot, creating sparks as the metal is compressed. Its glowing ingot, still semi-molten, reveals the intense heat required to maintain its plasticity before the cooling process begins. Utilizing 15,000 tons of pressure, the glowing ingot is flattened, showcasing the intense energy of the forging process. Under immense pressure, the superheated steel begins to deform, flowing outwards symmetrically as it is forged into its final shape. As the metal is forged, the intense heat and pressure force the grain structures to realign, creating a stronger, unified pattern. The extreme heat causes the surface to glow intensely, but as it cools, the refined texture and scale pattern. Precision is key as the forged part, still glowing from residual heat, is carefully positioned on the rails for the next stage of the process. This cyclical transformation is essential. The metal must be heated again, ensuring maximum durability before the cooling stage.
Make sure it's spotless.
All right, lowering the die now.
Hold it there, check the alignment on the left.
Crafted with micro-level precision, these dies are essential for creating the complex aerospace components of the future.
Inside the factory, precision placement ensures the glowing metal is perfectly aligned before the die presses down. The secondary forging process ensures the material fills the intricate aerospace geometry precisely.
The secondary forging process begins, refining the complex geometry of the aerospace component with immense pressure. After the secondary forging process, the press slowly opens, revealing the precision form of the new aerospace component. Dimensional verification is critical here. The technician uses a precision micrometer to check the aerospace tolerances of the cooling metal. The forged components are meticulously arranged before undergoing the critical heat treatment process. Utilizing immense force, the locking bolts engage, creating the perfect vacuum seal essential for the heat treatment process.
The thermal graph confirms the solution heat treatment is proceeding exactly as planned, with temperatures climbing steadily.
The robotic arm extracts the glowing components from the furnace. They immediately begin to cool, the color shifting rapidly from bright yellow to deep orange. This is the critical moment. The glowing component enters the quench tank, instantly cooling the metal in a burst of fire and steam.
This extreme close-up reveals the intense thermal dynamics as the superheated metal meets the cooling water, creating a dramatic phase change. Submerged in the quench tank, the metal undergoes a rapid transformation, the intense heat rapidly dissipating into the turbulent water.
The transformation is complete, but post-quench verification is critical. The technician meticulously checks the component for any The 5-axis head engages the workpiece, demonstrating the machine's capability to mill complex geometries with unparalleled precision.
In slow motion, we witness the initial cut. The friction generates intense heat as the carbide tool shears away the first layer of the blank.
With incredible precision, the coolant stops and the automated system exchanges the cutting tool and immediately retraces. At this magnification, we can see the ultra-detailed material removal as the chip curls away from the cutting edge in a continuous flow.
The coolant system is vital for thermal management, directing a precise spray.
This 5-axis machine represents the pinnacle of precision engineering, rapidly milling complex parts in a synchronized ballet of movement. The smooth, almost flawless texture you see here is the result of meticulous industrial machining, accurate to the micron. The automatic tool carousel rotates, selecting the next precision cutting tool with mechanical precision before locking firmly into place. The completion sequence finishes. The cutting tool pulls away, leaving behind a flawless surface finish on the component. Once the cycle is complete, the hydraulic jaws retract, freeing the newly machined gear for the next stage of production. Once the machining is complete, the aerospace part must be handled with extreme care to maintain its pristine finish. Utilizing advanced automation, the components are smoothly guided along the conveyor system for systematic inspection. The coordinate measuring machines, or CMMs, analyze the parts with micron-level accuracy, ensuring the highest standards are met. Ensuring the highest quality standards, the robotic arm performs a precise laser scan, guaranteeing the component meets exact specifications. This specialized probe utilizes a dual laser system to scan the component, ensuring tolerances are met. Here we see the ultrasonic probe being applied. The gel ensures maximum transmission of the sound waves for accurate flaw detection. Each approved component receives a unique serial number and certification code before moving to the next stage.